So far it has been argued that there is a way to calculate the force of viscosity on a blob that's out in space is basically to go around the surface of the blob and take this integral, where it's basically take this object that's the viscous stress tensor dotted with the surface normal times the area at that section of surface, and go through all of these sections and sum the viscous forces on each of these little unit areas on the surface, and this will basically get the net viscosity on the entire object. So that will ultimately get the net force that's caused by the flow around the object that generates these viscous forces of drag on that fluid blob. So the next step is basically to put this in the Navier Stokes equation. To put this basically in the Euler equation, and by putting this viscous force in the Euler equation, this will lead to the Navier Stokes equation. So to go back and go back over the Euler equation. So the Euler equation is basically this. This is rho, which is the density, which is mass per unit volume. Then the integral over the fluid blob volume at a given time that's following specific particles, say a kth particle. And then here, partial derivative of the velocity field with respect to time. And it's basically the advection term. It's the u vector dot gradient symbol and the u vector. Don't know what that thing was doing. U vector again. Okay. And then the dV for the volume. And this basically equals again the integral over the volume, and these are the force terms. So the force term is the overall force that's assumed to be dependent on the mass. So this could be the force of gravity or something. And then the force due to the pressure, or more precisely the gradient of the pressure. And then again, the integral is over the volume, so that's the unit volume. Okay, so this is basically, this side of the equation is basically the mass times the acceleration side. So this is basically just going to be force equals mass times acceleration. Of course, written in the other direction, mass times acceleration equals force. And this is basically the force side. So in order to convert the Euler equation, which is this, into the Navier Stokes, all that needs to be done is to add the force of viscosity to the force side of the equation. So these are the other forces, so it just adds in the force of viscosity, which is this. So this thing is plus, and then the surface integral, which is actually dependent on time. And that surface integral is, of course, the surface of the W blob. So to get the force viscosity is basically integrating over the entire surface of this thing to get the force. And since W depends on time, then the surface of W, which is S, is the surface of W, also depends on time. However, this can be simplified further, and the way to simplify it is to basically turn the surface integral into a volume integral. So the next step is to go through several steps that lead to simplification. So I want to take this integral, which is the surface integral, times the tensor dA, and I want to turn it, and it needs to be turned into something that basically is a volume integral over the volume W. So something dV. And the way to do that is basically to use Gauss's law. So use Gauss. Not sure if that's spelled correctly. So basically Gauss's law in general basically just says that if there's a surface integral and there's some kind of vector field dotted with this n hat dA, this thing equals the integral over the volume, but it's with the divergence of the vector field times dV. So this can almost be applied, but not directly, because the sigma is a tensor rather than a vector. So in order to apply Gauss's law, you need to work out each component. So for each component, example X, basically Fx equals mu, and the integral over the surface times t sigma x dot n hat dA. So basically this thing is getting broken down into components. So it can be seen that if n hat is dotted with each of these, it basically creates a 3 vector, and each of these components, the fx component just is a sigma x dotted with the n hat. And that's just by the definition of how the tensors and the dot product for the tensor is defined. So breaking it down into components, there's a sigma x dotted with the n hat. The sigma x is now a vector y quantity, so it turns out that can basically take sigma x is v. So just take this as v and then apply the Gauss's law. So doing that, or maybe what I'll do is I'll actually take it as v. Take as v. So this, what this does is this basically says f of x equals mu. Now this is going to be a volume integral. And of course the volume in question is the W volume because S is the surface of the W volume. And then it's the gradient dot product of sigma x times dV. Okay, so that accomplishes converting this. So this can also be done for the force on the y and the z. So that converts the surface integral into the volume integral. The next step is just notation. So notation. Definitions. So in order to make this easier to write, there's this gradient of a tensor that is basically just defined like this. And it's basically the divergence of each component. Divergence dot sigma y and divergence dot sigma z. So all that is notation. But basically what this leads to for f of x, it means now the force overall can be written in this, of viscosity can be written in this compressed form. It's going to equal the volume integral and mu, this new symbol, sigma dV. Okay. So that's a significant part of the simplification, but there's actually even more simplification that can be done. So this is more simplification. So it turns out that sigma in its original form was just a construct with of these velocity components and their partial derivatives. So sigma is really just constructed from all these partial derivatives of these ux's, uy's, and uz's. So that can be actually used to go ahead and do yet another step in simplification. So this is basically write sigma in terms of gradient is basically delta, various delta products of u. So what actually comes out is, and do yet another definition. So notation, definition. Yet again, this time this is going to be with u, and this is basically the gradient of a vector u is going to be defined as the following. The gradient of its x component, gradient of its y component, and the gradient of its z component. Which basically means that what happens is this vector actually expands outwards to a matrix. So this thing goes to basically 3 components. Three components. Oh, so this basically goes to D. I'll just write them out. Erase that. Ux dx duy or dux dy dz dux dz. So each of these expand out, and the entire thing actually goes out into a matrix of 6 components. So this entire thing ultimately becomes 6 by 3, actually 3 by 3. This will ultimately become a 3 by 3 matrix, essentially. Or you could call it a tensor. So what this does is this basically just expands each of these individual scalar components out into basically a row vector. And ultimately the entire operation basically takes this thing and expands it into a 3 by 3. What I guess would be a tensor, but it basically looks like a matrix. Is what this thing ultimately is going to go into. So using that definition, it turns out that you can take sigma, that was defined earlier, and sigma actually can be shown to be equal to this gradient of the u vector, if it is a gradient, basically delta u vector, plus delta u vector transpose. And all a transpose basically does is it flips about the center axis. So there's a matrix, it basically takes this and goes there and vice versa. So it kind of like mirrors the matrix about its diagonal is what it basically does. This is a transpose. That's what a transpose does. Okay, and then there's yet another step, and this is basically just at all of ours. It follows from basically algebra, the following. Can basically show that this gradient signal of the tensor actually equals the following. Gradient divergence of this guy plus this guy, the divergence of the u vector, and then the gradient. So this thing basically looks like a divergence. No, it looks like a divergence. However, obviously this isn't a normal divergence because this thing is actually a 3 by 3 object. So what this actually does is it takes the divergence of each of these vectors. So it'll take the divergence of the top row, and then the second row, and then the third row down. And what will come out of that every time it takes the divergence, it'll basically go ahead and convert that to a scalar. So clarify this a little bit more, what this thing is. So gradient dot grad u vector basically is going to equal, let me see what I did with that. So the gradient dot grad ux gradient dot grad uy gradient dot grad uz. That's what that thing actually is. Okay. So now taking this entire thing and putting this back into viscosity. So viscosity way up here was found to be this integral over the volume with the mu times this delta sigma or sigma of the stress tensor over the volume. That was the first viscosity. So basically putting this thing into that equation is the next step. So this turns out that first viscosity it was basically found to equal the volume integral gradient sigma dV. So this basically goes equals using this term of above and just write the whole thing out. Omega t, and then mu gradient dot, or divergence dot gradient symbol plus mu times this and dV. Double check that I did that right. Okay, so that's the force viscosity. That could be, this could actually be put into the Euler equation, and that would be one form of the Navier Stokes equation. There's also forms of the Navier Stokes equation that accept compressible fluids. However, in this special case, compressible fluids, the fluid is going to be incompressible. So for incompressible fluids, this is going to be equal to 0. Gradient dot u vector equals 0. Okay, so once that's done, so that basically crosses out this term. So the only term that's remaining is going to be this guy. Right here. So this is the only remaining term. The only term that contributes. Term. So ultimately, this is going to be the force of viscosity. I'll write this out. Green. So finally, force of viscosity for incompressible fluids is going to be this. So the integral over the volume and the mu times this funny gradient divergence term dV. Okay. So somewhere uphill should basically be the Euler equation. So this is the Euler equation. So the final result is going to be taking this term that has been just derived for force of viscosity and replacing the previous term in the Euler equation. I'm going to write the Euler equation again. Okay, so this is the Euler equation once again. Time derivative of the velocity field plus the advection term. This is the dV. This thing equals. And that's not on the force terms. So the overall force force minus the gradient of the pressure, which is basically the force caused by the pressure, V, and then add in the viscosity. T dot grad of U vector V. So that is finally the Navier Stokes essentially, except I can do one more thing. I can just move, since this is now a volume integral and a volume integral, I can just get rid of the volume integral and basically combine the whole thing. Okay, so that is basically an integral form of the Navier Stokes equation once I get rid of that one extra v that doesn't dv that doesn't belong in there. So that is that. Okay, so there's one last thing that to be done, and that is to note that the volume here is basically an arbitrary volume, so it can be made as big or as small and placed wherever it goes in the fluid, and this equation will still hold. So it follows from that it's actually possible to go ahead and effectively remove the integrals entirely and just write out the entire equation. Say that the integrands are equal to each other. So writing this out yet again. So just take the row. The time derivative of the velocity field plus advection term that equals the overall force term plus the viscosity term except I need to wrote that wrong. Need one more of these guys. This is the viscosity, it's just added, and then minus the gradient of the pressure. So I'm going to rewrite this one more time just to get the partial derivative of the velocity field with respect to time on one side and everything else on the other side. I think I'll use one more color. Okay. So I think I'll also move the row around. I don't want to put that one out because that's going to be negative. I should just put the G first. How did I write this? Okay, change the order one more time. Okay. I'm actually going to put the viscosity term first. And I'm going to divide everything through by the row term. And then the advection term is a negative because it's changed sides. Rho, the gradient of the pressure. And I'm going to put in one more comment since WT is all arbitrary. So basically it's because WT is basically an arbitrary volume that's possible to go from here to here for the term. So in the end, this is the Navier Stokes equation for the incompressible fluid. So I'm just going to write that out, and that finishes the derivation of the Navier Stokes equation. The next discussion will be basically what the physical implications are of this new viscosity term. And circle that, and this is the Navier Stokes for incompressible fluid.